Our next talk in the Understanding 2 conference comes from Professor Sorin Bangu from the University of Bergen. Sorin is a very dear friend. He's someone who's mentored me along the way and shown me the steps of, well, just going through things, and it's just amazing seeing him again and hearing the talk he's about to give. And that is titled Factivism in Historical Perspective. Misunderstanding the Gravitational Deflection of Light. Sorin, please take it away.
Thank you very much, Andre, and thanks very much to all of you who well, are generous enough to stay that long to listen to the talk. Okay, so I think I should get going if I can move the slides. Okay, fine. All right, so I should tell you right at the beginning that this is going to be an entirely of a critical paper. It's going to be focused on Hank Direct's theory of understanding, presented in a recent book. I understand that his views in this particular book is known, right? So people have heard of it. So although I'm not going to, it's a very good book, by the way, so highly recommend it. I'll not be sort of expecting you to have read the book already or have read it in like very carefully, because I'm going to summarize the important parts, at least the parts that interested me. Good. So the key question I want to address tonight, is whether past and false scientific theories, for instance, Newtonian gravitational theory, still provide an understanding of physical phenomena. So that's the key question, it's a puzzling question if you think of it. So I'm not, to be honest, I'm not entirely sure what I think of it, but we'll see what Direct thinks of it. So that will be our concern. Now, the answer he gives to this question is affirmative. As you can see on the slide, he says, although Newtonian mechanics has been superseded by Einstein's theory of relativity and is therefore strictly speaking false, it can be, and indeed still is, used to explain phenomena. And in this way, genuine understanding can be obtained, right? So, with this affirmative answer, Direct in fact subscribes to this idea in philosophy of understanding, which is called non-factivism. So according to non-factivism, scientific understanding can be obtained even on the basis of a false theory. All right. Now, what's the point of the talk, or what's my main sort of my main argument? Well, I'm going to apply, or so to speak, to test this theory of understanding on an astronomical phenomenon, right? The gravitational deflection of light. So I should also say that the Direct's theory of understanding is a theory of understanding why, or as he calls it, explanatory understanding, right? So it's to be distinguished from explanation, from understanding that, or understanding how, or there are other kinds in the literature, but this is his main focus. Good. So what I will argue, in effect, is that his theory delivers two opposite answers to our question, which is still on the slide, right? So the two answers are an affirmative one and a negative one, and that's already to create some tension. If you remember the answer that I said that he gives, which is only an affirmative answer, right? So the yes answer appears if we consider the structural aspect of the phenomenon, right? That there is deflection of light at all when it passes nearby the sun in particular. There's nothing special about the sun. This happens with other celestial objects, right? So the yes answer can be given in those conditions, but then there is the no answer, which can be given if we consider the what I call numerical or quantitative aspect of the same phenomenon, right? So the structural aspect has to do with the fact that the phenomenon that there is deflection at all, right? And the numerical or quantitative aspect has to do with the aspect of it according to which the angle of deflection has a certain value, right? The angle is very, very small. It's 1.7 seconds of arc. So this is what you have here on the slide is highly exaggerated. Moreover, and that's going to be what creates problems for direct theory, I think, is that this no answer, this negative answer, weakens his support for non-factivism. Now, another thing I should say at the very beginning is that this label, or actually those two labels, factivism and non-factivism, they don't appear in the 2017 book. So I checked this in particular. I'm not entirely sure why, but given the definition of the concept and given they actually appear, the level appears in other writings. So I took the liberty to attribute this position to direct. Now, I'll also say at the beginning a little bit about the historical situation when it comes to this phenomenon. So just I mean, I'm assuming that sort of familiar to everyone listening to this. It wasn't the title after all, so you knew what to expect. So the idea is that if we look at up in the sky, then certain very sort of a strange phenomenon happens, namely that we see stars which are somehow in the same line of view with the sun. We see them in a different position than they actually are, right? And this is because the light coming from them, the photons, the stream of photons, well, that gets deflected as the ray of light passes nearby the sun. This phenomenon was actually predicted by Einstein's general theory of relativity, and in 1915, and it was possible to sort of measure it and to confirm that the phenomenon exists, is out there, by two expeditions organized in 1919 by Frank Dyson and Arthur Eddington, so two English-British astronomers. So they went to basically to West Africa and to Brazil to observe this eclipse and to do the measurements, right? To confirm or to corroborate or to disconfirm the Einstein's theory, which predicted exactly this angle, 1.7 seconds of arc. It's a very sort of as I said, it's a very small angle, and it takes the instruments have to be very well calibrated. There has been some sort of maybe sort of controversy about what extent the experiment, this crucial experiment, so to speak, was convincing. Here is Ehrman and Glamour saying that in a very well documented paper that the eclipse expeditions confirmed the theory only if part of the observations were thrown out and the discrepancies in the remainder ignored. So I don't want to get into this controversy these days. This experiment is considered to be convincing, is considered to be definitive when it comes to Einstein's theory. Now, so that sort of historical fact is well known, I take it. The other fact I want to draw your attention to is maybe not so well known. And it has to do with the achievement of this physicist, fiercely looking and sporting a terrible haircut on the slide, Johann Georg von Soldner. So he's a physicist who worked in within the Newtonian framework, and in 1804 calculated the angle that the light gets, the angle by which light gets deflected. And he obtained this value, which is 0.84 seconds of arc, right? Which is half the correct value of 1.7 seconds of arc. That was the observed value and the confirmed value, that the experimental value, as it was, right? So von Soldner worked on this within, as I said, within the Newtonian framework, using all the Newtonian assumptions. Following Newton's idea that, which he presented at the end of his optics, the idea that the corpuscular theory of light, right? So if light is composed of particles, then even if they have very small mass, if you have this stream of particles passing nearby the sun, then they will be affected by gravity, just as ordinary matter is affected by gravity. Therefore, there should be some sort of bending, right? Some sort of a curved path that light follows. And then using the instruments, the mathematics, and the Newtonian theoretical apparatus, he calculated this angle to be half the correct value. Good. So we'll keep this in mind. I'll return to this achievement and to von Soldner a little bit later. Okay, so here is just to summarize where we are at this point. When it comes to Newtonian theory, von Soldner, and actually I should mention here Cavendish, about 20 years earlier, he also calculated this angle, got almost the same value. So within the Newtonian framework, we have that in this framework entails that light should bend because of gravitational attraction of the sun. So that's the structural aspect which the theory gets right. Now, when it comes to the numerical or quantitative aspect, since the angle doesn't have the correct value, is actually pretty wrong, right? It's half of what it should be. So the theory gets this quantitative aspect wrong. When it comes to Einstein, so again, he predicts and explains this phenomenon as a result of warping of space-time because of the presence of the sun. So you have like a big like a presence of mass energy, a big amount of mass energy that deforms the geodesics, and then light following like geodesics, then like itself has to be bent. So the theory gets this aspect right, and also gets the numerical quantitative aspect right, as we saw. Good. So so now I promised that I'll walk you through Dirac's theory of understanding. It's a quite elaborate and quite sophisticated. So I think I have, if I counted correctly, like something like 7 slides. So you'll have to bear with me. We'll go through it step by step. So this is what Dirac says. So his idea in the book is very ambitious and very, again, deploys a lot of like sophisticated tools of analysis. So his idea is to capture this elusive notion of understanding. That was a contested notion in philosophy of science, and I think Dirac does like a huge service to the philosophical community by trying to cast light on this, shed light on this, so to speak, on this idea or notion. So here is what he says: for scientists to understand the phenomenon P, it is necessary that they have an explanation of it based on an intelligible theory, and in addition, such an explanation is empirically adequate and internally consistent. Right. So those are the 3 conditions that Dirac imposes. Now, when it comes to intelligibility, I'll have a little bit more to say about it later. This is a feature that a theory possesses to the extent that it can be used by the scientists, right? How do scientists use a theory? Well, they use it to design explanations and explanatory models of the phenomena of interest. Intelligibility is, for the rector, a pragmatic feature and also a contextual feature. So the account that he proposes is contextualist. And the theories can be considered intelligible by a scientific community in certain contexts of application, but also may be deemed unintelligible by a different community. So this is what, in a different situation, right? So this is what makes the theory contextual. So this culminates into, with the proposal of what Derek calls the criterion for understanding phenomena. And I'm going to recite it. We're gonna recognize the three elements that we discussed about above. So CUP, a phenomenon P is understood scientifically if and only if there is an explanation of P that is based on an intelligible theory and conforms to the basic epistemic values of empirical adequacy and internal consistency. All right. Now, I need to say something about empirical adequacy, and I'm glad that Andre in his talk touched upon it. So it's a very important notion for Direct. And what I want to say is that, first of all, that for him, a certain explanation, in this case of a gravitational phenomenon, is empirically adequate when this explanation draws on empirical adequate theory, right? So that would be the Newtonian theory of gravitation, which I'll abbreviate as NWTG. Now, he also is committed to two other points when it comes to this Newtonian theory of gravitation. So he takes the theory to be empirically adequate, right? Which means that is able to save many appearances, right? To make correct claims, correct predictions about many observable phenomena. For instance, the phenomenon that light bends. And also, he says that the Newtonian gravitational theory is not a true theory. Because today we know that the unobservable structure postulated by Newton, the force of gravity, does not exist. Right. So this is how he presents things. Now, when it comes to the fact that the Newtonian theory is not a true theory, I totally agree. But I have some reservations about the first point, namely that the Newtonian theory is empirically adequate. So I want to distinguish here and to introduce this distinction between two kinds of empirical adequacy, and I will call it a structural empirical adequacy and the numerical or quantitative empirical adequacy. So that's a distinction that does not appear in the book, and does not appear in other places either. So that's something I want to introduce for the purposes of this paper and purpose of this talk. I think it's a distinction that is crucial here, and I think it's a distinction that makes a difference, and we'll see how it makes a difference in a moment. Good. So we'll get back to that. A little bit more about Direct's theory of understanding. So for him, intelligibility is a value, right? A scientific value, a value that scientists attribute to the cluster of qualities of a theory in one or more of its representation that facilitate the use of a theory. It's a context-sensitive value, and it's also a multifaceted, multiple realizable value, because different communities coextant or even across history may take different aspects of a theory to contribute to facilitating its use, right? It could be intelligibility was associated, and is typically associated with visual, should be able to pronounce it, visualizability of the theory, of the models of the theory, its appeal to causal mechanism, its unificationist character, mathematical simplicity. So all those things contribute to intelligibility of the theory. Again, he offers, similar to the previous criterion, he offers this criterion for the intelligibility of theories, which again you can see on the slide, runs as follows: a scientific theory and one or more of its representations is intelligible for scientists in context C if they can recognize the qualitatively characteristic consequences of T without performing exact calculations. So that's I recited verbatim this criterion. Now you can see a little indice there. Well, that's this is there because he mostly discusses mathematized theories. Now there are theories which are not mathematized, so for them there will be like a different indice, right? So more like there will be like a different version of this criterion, but the gist of it remains the same. All right, so we are done with Direct's theory of understanding, contextualist theory of understanding. I really hope I did justice to the complexity of the theory and to the sophistication. And now I will apply the theory to this, or I'll test the theory to this on this phenomenon, the bending of light. So the key question I will ask is whether, according to Direct's theory, we today understand this phenomenon by using the false Newtonian theory, the false Newtonian gravitational theory. And as I said at the beginning, I shall argue that the answer is both yes and no. And this is in tension with the only or the yes answer, the affirmative answer, which takes to be the only answer here. What I will argue more precisely is that Direct's theory entails that we do understand the structural aspect of bending, right? We do understand why there is deflection at all. On the other hand, I'm afraid that according to his theory, we do not understand the numerical or quantitative aspect of bending, right? In other words, we don't understand why there is that much deflection. Now, obviously, in and of itself, this is not a problem, not a big problem. It's just that the negative answer, which makes us think that maybe here we achieve only partial understanding. So this negative answer is a problem for someone like Direct, for a factivist like Direct, who wishes to argue for non-factivism. I think I called him factivist, but he's actually a non-factivist, right? So just to get this right. So in the end, the problem is that Direct cannot say without qualification that according to his theory, we understand bending by using the false Newtonian theory of gravitation. And this is what a non-factivist like him would want to say. So in my view, we understand it only partially. We understand its structural aspect, but not its numerical quantitative aspect. So let's see why that's the case, right? So let's see what is the argument for the two claims here. So the argument for the first claim is very simple. So what I'll do is basically take his theory and see to what extent the three conditions are satisfied, right? When it comes to the empirical adequacy of the theory in terms of in structural terms, right? The theory does explain why there is light bends around the sun, nearby the sun, right? Recall here we have to recall the type of work, the explanation that von Soldner's provided, working with the corpuscular theory of light. The theory, Newtonian gravitational theory, is internally consistent. I'm going to grant this. Now, when it comes to intelligibility of the theory, that's a slightly longer discussion. But I think that if we look at what the CIT, right, the criterion of intelligibility of the theories requires, then we can say that the physicist indeed can recognize consequences of the Newtonian gravitational theory without performing exact calculations. So remember that that was the condition that Direct associated with intelligibility, right? So from this perspective, the theory is, the Newtonian gravitational theory is intelligible. Why is it intelligible? Well, I guess the without calculation condition can be satisfied because there is, the physicists have always this analogy available, which will save them applying the actual law of gravity in any detail. So the analogy is between a cannon that shoots projectiles nearby the surface of the Earth, and someone who sort of opens a flashlight, turns on a flashlight nearby the surface of the Earth, right? So the idea is that both the cannonballs and the light corpuscles, yeah, will be deflected towards the larger body, right? In this case, the Earth, right? So they will both feel the force of attraction. So you don't need to go into any like particular calculations, because this comes out straightforwardly via this analogy from the very formula, right? You can see the how that's supposed to work. So when it comes to the intelligibility of the theory of the Newtonian gravitational theory, I think we can check the third mark, and we can conclude that a Newtonian, someone like a physicist working today within the Newtonian framework, with the Newtonian apparatus and the Newtonian tools, then such a physicist does understand the bending of light, but from this structural perspective, right? So that is the, in a way, the positive aspect of Direct's theory, that it does justice to this idea. Now, when it comes to the negative answer, I'm afraid we can argue that a Newtonian today, again working with the Newtonian gravitational theory, does not understand the numerical or quantitative aspects of this phenomenon. Although the theory is intelligible, it is internally consistent, it is not empirically adequate when it comes to actual quantities, that with the numbers, right, that it attaches to this phenomenon. So we saw before that from von Soldner's calculations, that the angle he obtained within using Newtonian theory is actually has the wrong value. Is almost half of the actual value that was observed, right? So Newtonian gravitational theory is not empirically adequate numerically or quantitatively. So here is the slide you've seen before, just to refresh your memory. So von Soldner calculated this angle, and it's not the right value. Good. So here is where we are at this point. A quick recap slide. If we consider this question, whether according to Direct's theory we understand this phenomenon, the bending of light, then contrary to the only answer he claims it's the right one, namely the affirmative answer, I claim that there are actually two answers available to us. One affirmative and one negative, depending on which kind of features we're interested, which kind of features this phenomenon, depending in which features of the phenomenon we're interested in, right? So the structural features, why there is deflection at all, or the numerical or the quantitative features, where there is a certain amount of deflection, right? So this poses a problem once again, because the negative answer poses a problem because Direct wants only the affirmative answer in order to provide support for non-factivism. Good. So let me go over some clarifications quickly, which would be more or less like answers to some possible objections that a supporter of Direct's account raise. So the first one is like this. So suppose that Dirac concedes that on his theory of understanding, the Newtonian physicist is entitled to claim today that she understands the bending phenomenon only structurally, that is partially. But he retorts that this amount of understanding is enough to score decisive points in favor of non-factivism. So the idea here would be that even if the objection I raised is maybe correct, it is rather superficial and maybe irrelevant, right? Now this is in line with some sort of gradualism that one can detect in his book. He talks in terms of in terms of like physicists having some understanding, or in terms of some degree of understanding. So I think a reply like this would be available to him, and well, actually a way to defend his position would be available to him. Now, in reply, I acknowledge that this kind of defense move is natural, right? So the past scientists, it would be somewhat strange to say that past scientists did not have any understanding of the phenomena they studied, in particular that Newton didn't have any understanding. So they must have had some understanding. So I grant that this sounds more reasonable. But on the other hand, I would point out that it is at best an open question whether having only structural understanding is enough to convince effectivists. And actually, in question here is not only a factivist, but anyone, right? Anyone who takes numerical or quantitative aspects of science to be fundamental will have problems with this partial understanding that we get. So they will say that such a result is, or this amount of understanding is not enough, right? So I admit that the argument the move I'm making here, it's the kind of objection and the reply is not decisive. It is, as I said, an open question, but I'm inclining towards the idea that this amount of understanding is actually not enough, right? So Dirac's theory would be in some kind of trouble here. Now, the other possible objection is that, or the other possible kind of I don't know, retort here would be that so supposing that he bites the bullet, right? So he says, supposing that he says that, well, fine, in the case of bending of light, my theory is in trouble because it entails that we only have understanding of the structural aspects, but we lack an understanding of the numerical aspects, and this partiality is a serious problem. However, the problem he might, or the issue he might raise is that this bending of light is kind of a one-off, kind of a singular phenomenon. Light is maybe special, and the problem does not generalize, right? So maybe, yes, there is this exception to my theory, but nothing is perfect. So the theory perhaps can tolerate this exception. I'm afraid that that the problem does generalize, and that there are other phenomena such that the Newtonian theory of gravitation gets their structural aspects right, but the numerical quantitative aspects wrong. So here is one other phenomenon, very important phenomenon, which I'll be discussing very briefly. Again, I take it that it is somewhat familiar to people in the audience, is the famous precession of the perihelion of Mercury, right? So here is the story. Astronomers have noticed that the perihelion of Mercury has or undergoes some sort of like a rotation, like a rotation move, right? So here is Mercury, right, in green on the slide. Here is the sun. Mercury moves in an ellipse around the sun, but the plane of the ellipse is not fixed, right? So it looks, it seems that, so that's been observed for centuries, right? That the plane of the ellipse is undergoing this kind of rotation. It's a very slow rotation. The angle, it's called precession, right? So it happens, I mean, the whole rotation takes 250,000 years to go all the way around, but it does happen, right? Now, Newtonian gravitational theory predicts this effect and also explains it. Is again a structural kind of prediction or explanation. The structural aspect of the phenomenon is right, according to the theory gets it right, is due to the various gravitational pulls, right? So the story has been well known. However, the theory fails again to get the numerical or the quantitative aspect right. So the theory, the Newtonian gravitational theory, and as astronomers have calculated it, gives the incorrect amount of precession, which is 5,557 arcs per century. But it's measured to be 5,600 arcs per century, right? So this level of precision, you can see, has been achieved over the years by astronomers through a lot of careful observation. So it looks like there is this 43 seconds of arc that's missing, right? So that is the problem of the perihelium, of the precession of the perihelium of Mercury, which could not be obtained through applying the tools of the Newtonian astronomy, but has been obtained by general relativity, right? So Einstein calculated this and obtained the exact value right. So again, I think if we go back to the objection, this phenomenon, the getting the structural aspect right but getting the quantitative aspects wrong, that's not a singular occurrence. There are others, but we don't have time to go into them. Now, I'm almost I'm very close to the end. I want to say one more thing about this idea that there is some sort of relation between understanding and skill, right? So that's also an important element in Direct's theory. And here is a quotation. It's not from the 2017 book, but it resonates with things you'll find in the book. So I'm going to read it because it'll both refresh your memory about where he stands, and also it will kind of stress the role of skill, right? So here is what it says. Newton's theory is, from today's perspective, false and does not describe reality. The attractive forces that Newton postulated do not exist according to Einstein. But does this mean that Newton had no understanding of gravitational phenomena? That seems an unacceptable claim. So we face the dilemma of either giving up the idea that understanding requires truth, or allowing for the possibility that in many, if not all practical cases, we do not have scientific understanding. I'll argue that the first one is preferable. The link between understanding and truth can be severed. This becomes a live option if we abandon the traditional view that scientific understanding is a special type of knowledge. While this view implies that understanding must be factive, I avoid this implication by identifying understanding with the skill rather than with knowledge. Okay, so I have a couple of things to say about this quote, which I take to be representative. First of all, that I agree with the spirit of this. I think that appealing to skill is very important. However, when it comes to the kind of issue I raised, invoking skill does not change anything actually. So, and this is why, and then the reason why that's so is because those passages again don't look at the whole picture. Right, the whole picture consisting in having sort of two parts. That there's a structural understanding. There is a structural aspect of a phenomenon, and then there is a numerical quantitative aspect. Right. So The Newtonian physicist, I grant that the Newtonian physicist needs skill to massage a prediction and an explanation of the structural aspects of phenomena out of a false theory, right? And that this exercise is definitely pedagogically useful, as Direct and one of his collaborators pointed out in a paper. I think that's the right thing to say. However, I would add that no amount of skill can turn 0.84 seconds into 1.7 seconds. No amount of skill can turn 557 seconds into 5,600 seconds. So when it comes to those numerical values, no amount of skill can help Newtonians get the numerical or quantitative aspects right. So the skill, when it comes to the kind of issue I raised, becomes, I mean, the appeal to skill becomes irrelevant. But if this numerical or quantitative understanding is missing, then the non-factivist, or in this case, Direct's case for obtaining scientific understanding from a false theory is quite weak. I'm not saying it's completely destroyed, but it's weak and significant. I'm pretty much done. So here is a quick review summary of what I've been talking about. So I discussed critically Direct's theory of understanding, which is based on his two principles, the two criteria. That theory is supposed to entail that we today understand the bending of light by using the Newtonian theory of gravitation, as he actually said it. And since this theory is false, as he acknowledged, this would be a case in favor of non-factivism. What I argued, just simply by applying the theory, is that that theory of understanding, I argued that this theory only entails that we understand the structural feature of the bending, but not its numerical quantitative feature. So this would amount to a partial understanding of bending, and also that this amount of understanding, so to speak, is not enough to convince anyone who stresses the quantitative nature of science. And this includes the factivists. And also that this bending is not a singular, is not an exception which can be ignored. Therefore, I think it follows that Direct's claim or his case for non-factivism is weak or incomplete. Now, this is not the end of the story, but I'm not going to get into this at all. That's the last slide. This is not the end of the story, because, of course, one might ask questions like the ones you have on the slide. Well, is there still hope for non-factivism? Are there better arguments for non-factivism? And my answer is yes. I'm a non-factivist, by the way, so now it's time for full disclosure. So I'm in a way with Direct on this, under when it comes to the big picture. And yes, there are better arguments for non-factivism, arguments from idealization, right? From the idea that, from the remark, the observation that science appeals to idealizations in order to formulate explanations, and therefore there is room for falsehood to contribute to our understanding. That's a line pushed for many years by Catherine Elgin and I think Angela Potocznik more recently. I think it's the way to go, not the historical argument. But again, in fairness to Direct, I should also mention that he pursues this argument as well, the argument from idealization. There are some chapters in his book where he argues along those lines as well. So non-factivism is not dead. It might actually be alive and kicking. So that's all I had to say. Thanks very much for your attention.
Mulțumim și noi, Sorin. Thanks so much for your talk, and I'm sure everyone's joining me in using the virtual applause button. Or if they're not, they might be applauding in their own homes. I
hear all the applauses.
Excellent. And so if you'd like to ask Professor Bangu any questions, please make yourselves known either via a virtual hand or making yourselves known in chat.
I stopped sharing the screen, but I'll be happy to reshare it, so to speak.
Okay. I wonder if there are any questions. So I have a couple of questions of my own, but I don't want to abuse my privilege as a chair for the time being.
Andre, go ahead.
Okay, so it seems to me that this distinction you draw between structural and numerical empirical adequacy is really interesting. And so naturally, once you have a powerful tool, you want to see it at work, right?
Yeah.
So would you envisage other specific cases in the history of science where you would see this distinction at work, or would you see this distinction as undermining, say, traditional arguments in favor of realism or in favor of anti-realism, or how would you see it at play in other debates? How would you see it as changing them?
Yeah, I've been thinking about this. I mean, to what extent this idea sort of crosses over into other debates. Well, I think first of all, I think it might have some sort of relevance for von Frussen's constructive empiricism, right? So because I didn't say this in the talk, but again, I take it that this is well known to everyone, that empirical adequacy is a concept, was a notion that that von Frussen introduced in his classic now 1980 book. But the way he presented it there was not the way I presented it here, right? So empirical adequacy is supposed, or theory is supposed to be the feature of the, or the quality of that the theory has to tell us true things about, to get the observable phenomena right, to make true predictions about observables, right? That's very important. Now, I think that this can be refined because we can have kind of two kinds of observable phenomena, right? So one is like the structural, if you want, the qualitative type of phenomena, such as the fact that light bends, or that planets orbits undergo that precession. So that's the qualitative or the structural aspect of the observable phenomena. But then there is another aspect of the observable phenomena which is also observable, and then we observe a certain value, right? We observe we can determine experimentally a certain value. So I think this might have some kind of relevance for constructive empiricism. And insofar as it has this relevance for constructive empiricism, then maybe spills over into the debates on realism and all this. When it comes to other phenomena in which this distinction appears, I don't know. I mean, I have in mind, for instance, the second law of thermodynamics, which, of course, at an observable level, we will never see a reversal that the law bans. But then we also know from statistical mechanics that this is in fact a very low probability, like a minuscule probability for the reversal type of phenomena to happen. So this is another, if you want, a quantitative or numerical in terms of probabilities, right? Classical thermodynamics does not have any probabilities associated with it. So that would be an observable phenomenon, which is, as I they call it, like more like along the lines of the structural, right? So it's a qualitative. You'll never see a reversal, right? So although on the other hand, if you look at things from a different perspective, a reversal is possible, although it's highly improbable. So that would be another case. Yeah, I'm actually interested. So if you
okay, quick question, very simple and undergrady. So Copernicus in proposing his view thought that the trajectories of planets are circular, right? And then Kepler says that they're elliptical. Is that a structural or a numerical change, or both, or
well, to the extent that they both, I mean, yeah, that would be an interesting question to decide. I mean, what they had, I mean, the structural aspect of the phenomenon was that those orbits were around the sun, right? So that's crucial. Now you have this more like quantitative or numerical, if you want, element that they are ellipses and not circles, right? So maybe that is another application, right? But the difference here would be that unlike the Ptolemaic people and astronomers, well, they got the structural aspect wrong, right? So that would be a major difference from this particular case, in which Newtonian mechanics still gets, I mean, in terms of the examples I discussed in the talk, Newtonian mechanics still gets the structural aspects, the qualitative aspects right. And that's very important. That's what makes it still kind of a good candidate, or a good topic to teach in I don't know, high school or even undergraduate physics classes, right? So because if you think of this question, or the initial question, can we get understanding through that? It's a hard to answer question, because if the answer is no, period, then you wonder, okay, so why do we teach those theories then? Well, they have a certain value, which is as I mentioned, it could be pedagogical, but they also get a lot of the things right. I mean, the structural things right, and also in some contexts, when we were discussing like a context in which like speeds are rather low, right? So it gets even the numbers right. Well, numbers with certain approximation, right? But still, there will be the numbers will be correct. If you kind of look at the numbers with the maximum sort of accuracy, then they will not be correct. But within a certain experimental error, the numbers are typically correct in many cases, right? Not in the deflection case, not in the perihelion case, not in other cases, but in some other cases, Newtonian mechanics gets even the numbers right. So that's the reason why we're still using it, where we're still teaching it. Okay, so I see there is a question, but yeah. So
yeah, this is really interesting, because I think the classical line is that at early enough, right, in the game, people were a bit unsure, because the empirical adequacy of Copernican astronomy and of Ptolemaic astronomy was comparable.
Oh yeah, absolutely.
And so, and so what you're saying is, no, it wasn't. Only the numerical one was, the structural one wasn't. Yeah. Okay.
Well, so the way people talk about this is in terms of, okay, so the Copernican theory was empirically adequate, right? No, I mean, there is no discussion of this kind of a distinction between structural empirical adequacy and numerical empirical. So put that aside. So what people say is that, and people like Van Frost and all, they say, well, that is that theory, the Copernican theory was the Ptolemaic theory was empirically adequate, right? But it was not true, because it didn't get to the truth of the matter, namely that the Earth goes around the sun, and so that would be the deep structure that the theory didn't get right. However, you could make correct predictions with the Ptolemaic theory, and as long as it saves those appearances, right, that you could see could predict where the planets will be in the sky and things like that, then the theory is empirically accurate. Obviously, the Copernican theory is also empirically adequate, because you can also make predictions. we'll put aside the fact that you need to use epicycles as well. So, but that's only between us, right? So we put that aside. So the theory is empirically accurate, and it's also true, right? Because unlike the Ptolemaic people, the theory gets the fundamental structure of the solar system right. It tells us that that the Earth, the planets, orbit around the sun, right? Move around the sun. So that's the way people sort of kind of, you know, like cut the pie here, right? There is a longer story when it comes to the distinction I wanted to push here between structural empirical adequacy and numerical or quantitative empirical adequacy.
All right, thank you so much, Sogin, and that sounds like an incredible distinction. So I'll definitely want to read the text as well. Next up, we have Heinrich Blatt. Heinrich, please go ahead.
Okay, thank you. Yeah, I have actually two questions. I would have one regarding graduality. I'm wondering, by distinguishing the structure adequacy, do you introduce kind of graduality by this one, by going kind of some paths between circular orbits and elliptical orbits and then to Einstein? What do you think?
Well, I introduced gradualism in relation to the idea that I mean, it was like a defense. I was sort of, well, trying to organize some defensive line on behalf of Direct, right? So he might say something like this: look, fine, even if you are right, and my theory does not entail or does not yield this numerical understanding, still gives us this structure understanding, or if you want, qualitative understanding, right? And this is some understanding, right? There is something. This is still something. So this is the gradualism I had in mind, right? And he talks about, in terms of some understanding, some degree of understanding in the book. So I thought that wouldn't be absurd to argue on his behalf, as it were, and reply to my point along those lines, right? So to say that, well, I'm a gradualist, my theory yields some understanding, therefore you should be happy, or effectivists should be happy with this, because, okay, it's enough, right? And the question was, the next question was, is it enough? Because it might not be enough. Here, I didn't want to be like super, I don't know, have like a decisive or an absolute kind of position. I'm not sure if it's enough. To my mind, it's not enough, but that's maybe only me, right? So I would think that, on the other hand, I would think that anyone who is interested in those quantitative aspects would be unhappy. So they would say, no, it's actually not enough. You need to get the numbers right as well, right? So this gradualism would not, in the end, my position was that it would not help him that much. It didn't have, I mean, Andrei introduced this interesting idea, the difference between circles and ellipses. You might see some sort of like a gradual way of deforming one into the other. That had almost nothing to do with the gradualism the way I talked about it, right? So it was a gradualism in a way applied at the level of the kinds of understanding that that Direct's theory produces, right? One would be structural, the other one would be numerical or quantitative, right? So yeah.
Okay. Then I would like to add a second question, if I may. Is this okay? Okay, this is regarding your other concept regarding the quantitative how the numbers suit, basically. So
yeah, the quantitative aspect of the phenomenon, yeah.
Exactly. So by what do you say that we have kind of the true values? Isn't there some problem where you run into if you say like, okay, we have now the correct numbers, or from where do we know that we have the right numbers and not just some preliminary numbers as Newton had? Because I mean, also the guy who calculated the light deformation according to Newton's theory also did it to his best knowledge.
Yeah, so I have this kind of well, if you want, absolutist view of numbers when it comes to this case. I think that this is the correct number, the number that won't be changed. So yeah, I think that those are the true numbers. They might not be, but honestly, I don't think that. So there could be like other experiments more refined, and they would find maybe other numbers. But as far as the current physicists are concerned, those are the numbers, and they're the true numbers, and we'll have to. I mean, any kind of judgments or any kind of theories we produce in philosophy or in physics have to take those numbers into account, right? So yeah, I'm very kind of I would stick with those numbers, right? So the number that the Eddington expedition found is there to stay forever. The number that von Soldner and Cavendish and others calculated is wrong. I'm tempted to take this to be the end of the story, right? Yeah, maybe it's not so, but as far as I'm concerned, and I think as far as the physics community is concerned, those would be there forever. I mean, okay, never say ever, but because we know that things change, but certain things maybe don't change. So yeah.
Okay, but this means that understanding would need to be revised if numbers also get revised.
Yeah, that's an interesting question. I mean, so what would happen if tomorrow? Well, I mean, what we would say that the general theory of relativity, Einstein's theory, which produced the number which we take to be the right one, will turn out not to be empirically adequate when it comes to this numerical quantitative aspect of the deflection phenomenon, and that's always possible, right? We know that science progresses, and maybe this if we find a different number, then we have to go back and acknowledge that the theory is not empirically adequate when it comes to this this quantitative aspect. In the same way in which Newtonian theory, we have to say this about the Newtonian theory these days, after we found out the correct number, because that's an interesting aspect I didn't mention. Before the angle was measured precisely to be 1.7, there was kind of agreement that first of all that there is deflection, and then that maybe the amount of deflection is the one measured by von Soldner, right? So they didn't have a better number. So before the general relativity and the Einstein's prediction and the eclipse expedition and the calculation, all that, before all this, then the Newtonian gravitational theory produced both types of understanding: structural understanding and understanding of the structural aspect and of the qualitative numerical aspect. Because there is no competitor, right? There is no way to argue against that particular number. But after general relativity came along, then yeah, at that point we have to acknowledge that the Newtonian theory produces only partial understanding according to direct, right? So that's also important qualification.
Thank you very much for your clarification.
Welcome.
All right, thanks so much, Heinrich and Sogin, for answering. very quickly, right at the end, we've already abused your patience and we're 30 minutes behind, but really quickly, I just thought I'd defend you and Hank and Kate Elgin, people I care about. So just non-factivism about understanding, right, is the claim that truth is not an empirical norm that's required in order to understand something scientifically or whatever, right?
Right.
And so somebody, yeah, just to finish the thought. So somebody,
right. Okay.
who, yeah. So somebody who denies non-factivism, in some sense, incurs the burden of proof to say that truth has to be a norm for understanding, and quasi-factivists, the way I read the sort of older literature, have shouldered that burden and have tried to say that, look, there's a difference between the literal contents of models and their explanatory content. And if you look very closely and carefully at the explanatory contents, you'll see that that has to be accurate in some sense. And so there was always this kind of feeling in the background that they need to take on this burden of proof, and that the default position is in some sense a kind of prima facie non-factivism, right? So if we recall the Aristotelian worldview, well, that's clearly radically false by our lights, but it gave us some seeming understanding of the world. And then we move on a little, and Descartes has his own worldview, and that gives us some seeming understanding of the world, but clearly also radically false, and so on, right? So always the quasi-factivists are on the defense here. And when you yourself, so that's sort of one little dialectical point there, right? And the second one is this: when you yourself say that, look, maybe Hank got this particular case study wrong, I'm not competent enough to judge who's right here, but suppose that that's right. That doesn't mean there aren't a plethora of other cases where he gets it right, and a single case suffices to make the non-factivist case, right?
Okay, so a couple of things here. I'm not entirely sure who has the burden of proof between factivists and non-factivists. It's pretty clear that I would say, to my mind, that it's pretty clear to me that given how central idealizations are in science, and that idealizations are essentially falsehoods, then it seems as if the non-factivist is like the default position, and the factivist or the quasi-factivist have to do something about that to account for how that is possible. So that's one thing. Another thing is, well, when you said that the Aristotelian theory and the Cartesian theory and all those theories produce some understanding, well, you have to be careful, because you also have to say according to which theory of understanding, according to what theory of understanding. And I mean, as I said before, Hank Directs did like a huge service to people working in this area, because he pinned down, he basically stuck his neck out and told us what he takes understanding to be, right? So those two criteria and all that. So it remains to be seen whether, according to this theory of understanding, Aristotelian physics provided understanding. That's a topic which is again a different story, different discussion. Right. It remains to be seen whether Cartesian physics provides understanding, what kind of understanding, again, according to one particular theory of understanding. So all those things have to be judged always, I would suggest, always in relation to some particular understanding of understanding, right? Because yeah, we all have intuitions, we all have kind of hunches and all this, but they have to be in a way, tested, if you want, or judged in relation to some particular well-specified account, such as direct. Like, there are probably other people who come up with some theory of understanding, but until now we have this one, and we'll try to make do with. Yeah.
All right, and perhaps you yourself will contribute more to this literature. That would be fantastic. And please.
I should say one more thing, which I forgot. It's quite important, namely that Direct discusses the deflection of light in the book, right? There are some passages about it, and some detail provided there. But so I did not bring this phenomenon or this kind of issue out of nowhere.
Right.
But nothing he says in the book can function as a retort or as a reply or as a refutation of my points, as far as I'm concerned. And maybe I should have put this on the slides, in fact, because or make it clear in the presentation, because yeah, shamefully I completely forgot to mention it, that he does take it up, and is aware that might be an interesting phenomenon to discuss.
Well, just as a last quick comment, it seems to me that once you reconceive of empirical adequacy, that tends to upset any traditional balance between truth and empirical adequacy. And so many of the traditional debates and viewpoints are going to need to be reconceived if your distinction really and ultimately holds water. So it just seems to me like this is a gold mine, and I'm incredibly happy you presented this. So, yeah.
Well, thanks. I hope that you're right. Yeah. So you can have numerical truth and structural or qualitative truth about a lot of things, right? So this is really, I mean, this is not new. We knew this since forever, right? But in this case, seems to be relevant. Yeah.
Right, but the idea that structure preservation across transformations is something akin to empirical adequacy, I think is well, sort of novel. So yeah. Anyway, thank you so much, Sorin. Please join me once more in thanking Professor Bangu for his talk, and this was absolutely spectacular. So with that, our conference has come to an end. I'm very grateful to all speakers and to all members of the audience for your questions, for your comments, and this has been amazing. Thank you. Take care of yourselves. These are troubled times, and it's important that you do that. Good night.
Thank you. Thank you. Andrei, can we talk a little bit afterwards? 2 minutes?
Sure thing. Sure.
Okay, perfect.
It's my pleasure. Thanks again.